Thank you very much for the very exciting introduction. And thank you for the invitation to talk in this very nice seminar. Today I'm going to talk about algebraic geometry and a little bit beyond, outside algebraic geometry. The discussion would be relatively general. I will, of course, talk about mathematics. But these are the kind of stuff which are a little bit old, so it's not like the latest kind of research in algebraic geometry. But I think it's good for people who are not experts in the subject. So this is more directed at non-experts. Let's start with ancient history. Babylonian mathematicians, they solved equations thousands of years ago. In fact, like 4,000 years ago, they already knew how to solve, for example, quadratic equations, degree 2 equations. And some of the reasons they came up with this kind of equations to study were basically practical. So let me just give you an example how they came up with that type of problem. For example, suppose that we have a rectangle which has length x and width y. And suppose that we already know the sum of the two sides, or all the sides of this rectangle, and we also know the area of the rectangle. So this could be, for example, a piece of land somewhere in Mesopotamia. Now, having these two numbers, x plus y and x times y, they wanted to recover x and y to see exactly what x and y are. Now you can change the equation a little bit. What we can do is we can put, so we know that y is equal to b over x, because x times y is equal to b, and x plus y is equal to a. So we get this new equation. Instead of y, we can put in b over x. So we have x plus b over x equal to a. And if you multiply both sides by x, then you end up with this quadratic equation, which is x squared minus ax plus b. Now we have a and b, we want to calculate x. And if we know what x is, then we can also calculate y. So this is one of the reasons they came up with equations, like degree 2 equations, like 4,000 years ago. And they knew how to solve these things. So this is a tablet, Mesopotamian tablet. I'm not 100% sure if this is about this particular kind of problem, but this is a sample text. So this is quite impressive, because even in this day and age, people in high school learn this kind of equation. And you don't learn it in like primary school. So that means that they were doing actually something quite non-trivial 4,000 years ago. So this has a very long history, and of course after them a lot of people try to also solve equations of higher degrees, for example degree 3 equations and degree 4 and so on. It took like thousands of years, almost 4,000 years. And this quest for solving equations, it led to the development of several areas of mathematics. One is obviously linear algebra. If all your equations have degree 1, and if you have like more than one variable, then you are just doing linear algebra. And we know that even this subject is not very, very old. So maybe mostly developed in the last 19th century, or maybe a bit before that. It has to do with matrices. And then we also have algebraic geometry, when you have equations, especially if you have a bunch of equations, not just one. And if the degrees increase, then everything becomes more complicated. You get algebraic geometry. But if you work with, for example, rational numbers, then the same questions also come up in number theory. So all these things have overlap here. So essentially, we like to look at polynomial equations. So you can define algebraic geometry in a very simple way as the study of solutions of systems of polynomial equations. Now, different parts of mathematics deal with different type of functions. In fact, the type of functions that you study in a subject almost maybe determine the subject. For example, if you work with arbitrary functions, then you are basically doing set theory. But if you have topological spaces and you want continuous functions, or even just you study functions over real numbers or the real numbers to the power n, or for example on the plane or in the space, then you naturally get topology. But if you have like holomorphic functions, then you have analytic geometry and so on. So what distinguishes algebraic geometry from the rest is that almost everything is built from polynomial equations. And so from that, you can get a lot of algebraic, but also geometric structures. And naturally, the subject is related to many other parts of mathematics because polynomials are very basic. So they just appear in almost every part of mathematics, but also outside mathematics, like physics, computer science, economics, and so on. But the funny thing is that all the polynomials, in a sense, in a superficial sense, they are maybe the simplest type of functions, but the geometry that you get out of these so-called simplest functions happen to be one of the deepest and most complicated parts of mathematics. Now, to do algebraic geometry, we need to start with a number system. That is just a set of some kind of numbers with a reasonable structure on it. To be more precise, we need to start with a field. Now, mostly we work with these examples. For example, we can start with the rational numbers, we can start with real numbers or complex numbers or even finite fields. So as soon as you have a field, you then get algebraic geometry. More modern algebraic geometry, in fact, can work even with arbitrary commutative rings. So you can even start with rings and build algebraic geometry on top of that. But let's just stick with these familiar examples of fields. Okay, so we have our fields and we want to study polynomial equations over this specific field. The first thing then we can do is just put all these polynomials together and get a ring. So we have k, this is the field, t1 to tn are independent variables, and this kt1 to tn is the polynomial ring in these variables over this specific field. So this is the algebraic side of the story. But we also have a geometric side of the story, and that's why this is called algebraic geometry. You have algebra, you have geometry. This is the algebra here. Now we also have a geometry. Now, an affine variety, so this is a kind of geometric space, which is like the main object in algebraic geometry, is the common solution of a bunch of polynomial equations. So I can write it down as saying that you have your field K, you look at all the points with coordinates which come from this fixed field, so that if you put in these coordinates into all these equations, they will vanish all at the same time. So the common solutions of a bunch of equations. You can take finitely many or even infinitely many, would not make much of a difference. And so this is an algebraic variety, and this is something actually we already see in high school. So although algebraic geometry is a kind of complicated subject and mostly taught in later stages of undergraduate, or in many places not even taught in algebraic in undergraduate, but in fact we already see it in high school. So for example, if you take k to be the real numbers and f to be some simple polynomial and look at the graph of this polynomial, which we have all done in high school, that's an algebraic variety. But the difference is that the kind of properties that we are interested in algebraic geometry, usually they don't consider those things in high school. Now, everything about this geometric space X is actually encoded in this following ring, which is just you take the polynomial ring ktn to tn and divided by the ideal, which is generated by this f1 and fr. So that's why we have algebra and geometry, and there is a kind of dictionary. You can go from the geometry to the algebra, or from the algebra to the geometry, and see there is always a translation of properties, geometric and algebraic. And this duality, this dictionary, is what got me really interested in the subject, because I was really just fascinated how you say something very abstract in algebra, in commutative algebra, and then you see its geometric meaning, which is much more visual, much more intuitive. Especially in my case, I learned commutative algebra before algebraic geometry. So then I was very excited when I knew something in algebra and I saw its geometric much more the kind of thing that made more sense. It's just more visual. So it was this really interesting, this dictionary. Now, in general, the goal of algebraic geometry is to understand the local and global geometry of this kind of spaces, X, with respect to polynomial functions. So you mostly focus on polynomial functions. Now, let's look at the first, the simplest case, when we have only one variable. Let's take kt. These are polynomials in t with coefficients in k. So we have just one variable. And suppose that we have a polynomial. We want to find the solutions of this polynomial. So this is much closer to high school. As an example, you can see that t squared minus 3t plus 1, this has no solution in Q, but has solutions in R, which we can write down precisely. So this is the Babylonian kind of algebraic geometry. There is a formula, and these are exactly the roots, the solutions of this polynomial equation. But another simple equation like t squared plus 1 has no solution in Q and has no solution even in R. But like some 100 years ago, people forced a solution for this polynomial. In other words, they just imagined, they created a new kind of number, which is a solution to this polynomial. And that's how this whole complex world of analysis and geometry was basically born, because we had a polynomial, we just wanted a solution. And that's how complex numbers were invented. So in this case, then we see that the solutions are just plus and minus of the imaginary number, square root of minus 1. And now in general, if you have a quadratic equation, t squared plus p bt plus c is solutions in the complex number field can be found by this formula, again, with this high school mathematics. And then the natural question is, can you do the same for every degree, not just degree 2? Can you do the same in degree 3, for example? Can you find all the solutions and write them down in this form? Can you do that with degree 5, 10, and 2000 or not? This kind of question then led to the subject of field theory and Galois theory. And Galois theory says that, yes, you can do that if the degree of your polynomial is at most 4. But in general, you cannot always write down the solutions simply using a radical, like in the formula. So Galois theory is basically some kind of elementary algebraic geometry, but even this elementary form is already quite interesting. In fact, it's considered to be one of the most beautiful examples of truly modern abstract mathematics. And here is a picture of Galois. But the question is, what happens if you have more variables, not just one? Well, then as you can expect, everything gets more complicated. But let's just look at some simple equations like this one, t1 squared plus t2 squared plus 1. This is a polynomial over the rational numbers. It has no solutions over Q or R, simply because these numbers will always be non-negative. But it has solutions over C and also over finite field like F3. But on the other hand, if we just change this plus here to minus, we get t1 squared plus t2 squared minus 1. And this is the equation of a circle as we know from high school. And its solutions in R exactly give you, in R squared, give you the circle. But if we now replace these two here with m, we have t1, m plus t2, m minus 1. For m, at least 3, this has only trivial solutions in Q. So that means that any solution will either have t1 equal to 0 or t2 equal to 0. As you know, this is the statement of the Fermat's last theorem. So even this very simple, innocent-looking equation can give you hundreds of years of work. And that's the great thing about algebraic geometry. Simple equations can lead to a really deep and difficult mathematics. Let me also just give you this example where we have two equations, not just one. We have now 3 variables and 2 equations. This t2 minus t1 square and t3 minus t1 t2. If you look at the solutions over C, then the interesting thing about this example is that you can write down all the solutions. You can parameterize all the solutions by elements of the number field of the complex numbers. So that's why it's interesting, because you can parameterize all the solutions. Anyway, in general, if you go outside the complex numbers, if you work, for example, over the rational numbers, in general, it's quite difficult to see whether a system of equations has any solution or not. But if you work over the complex numbers, this becomes an easier thing. So in general, that is not the issue, whether there is a solution or not, but the issue would be, what is the shape? How is the shape of the space of solutions? And then that's how the geometry gets involved, and we can visualize the set of solutions and use our intuition. So our brain, the human brain, is very visual. It's very powerful when it comes to visuals, and we want to take advantage of this powerful visual intuition to get information about these algebraic sets, these affine varieties. Okay. So again, let's go back to this duality between algebra and geometry. We know that a line, the points on a line represent the real numbers. So each point corresponds exactly to one unique real number. But in the plane, a point corresponds exactly to a pair of real numbers. And you can do the same if you go, for example, to the 3-dimensional space. A point corresponds exactly to 3 real numbers. You can formally define something similar in every dimension, where now if you have a field K, for example, the real numbers, then Kn will be just points with coordinates coming from the field. So you can essentially pretend that this is a geometric space. So algebraic varieties, like affine varieties that I defined, they live inside these large spaces. And then you can ask the question, if you have an equation, how is the shape of this equation? So for example, the circle that I mentioned before, the shape of the circle, this equation t1 squared plus t2 squared minus 1 in k squared, it will look different if you work over different fields. It just depends on what k is. So over the real numbers, a circle would just look like a circle, what we know as a circle. But if you work over the complex numbers, you instead get a sphere, but with some points removed. If you work over finite fields, you get just finitely many points. For example, over F3, you get just these 4 points. So the shape, visual shape, will look different when you work over different fields, but still we can use this, our intuition, to say something about the geometry and then use the algebra to prove what we think should be the case. Let's also give you some more example of shapes of equations. In this case, we have t2 squared minus t1 3 and t2 squared minus t1 to the 3 minus t1 to the 2. We can draw the graph of these equations in the usual plane, and they look like this. These red curves are the graphs of this equation. So these are exactly the kind of thing we already can see in high school. But the thing is that in high school, maybe no one told you that this curve, this shape here, has a singularity at the origin. And similarly, this shape also has a singularity at the origin. So we can say something about these shapes which were not discussed in high school. We talk about them in a different sense. I will come back, I think, to these points. Yes, to singular points. Again, I use the same two equations. And as I said, these two are both singular at the origin. And there is a mathematical reason for this. You can characterize this property of being singular. And in this case, it's simply because if you calculate the partial derivatives of this function f, so derivative of t1 and t2, and see where these derivatives vanish at the same time, you see that that's exactly at the origin. And that's why we say there is a singularity. So you see that there is a geometric reason, there is a visual reason for this being singular. You can see it, but there is also an algebraic reason. There is a precise algebraic formulation of this phenomenon. And that's what makes algebraic geometry really interesting. Now, if you have singularities, then you can ask whether you can remove the singularity somehow. And that happens to be the case in most interesting cases. So for example, let's go back to this example of singularity from the previous page where we have a singularity at the origin. There is a process, an algebraic geometric process, which is called a blow-up. Now, I don't define what it is, but just intuitively what it does is it replaces this point with a line. And then it modifies this red curve. The red curves become something like this. And you see that here there is this singular point, but here we don't have singularities. So this process removes or resolves the singularities of this geometric space. So in this example, it's very clear to see, at least if you just know what the definition of a blow-up is, you see immediately why this is the case. But the amazing thing is that this happens to be the case in much more general settings. But for example, in this other example, where now I take t1 squared plus t2 squared plus t3 squared, I take this equation, its set of solutions will give me a variety x inside c to the 3. We can see that this is singular at the origin again. We know that one reason is because if we look at the shape, this is actually the shape over the real numbers. So even by looking at the shape over the real numbers, we can see, at least we can sense, there is a singularity here, there is something strange. But if we apply the same algebraic techniques, if we calculate the partial derivatives of this function, t1, t2, and t3, we see that it vanishes at this point. And so that's why we know precisely that there is a singularity, but we can also see it from the shape. And a similar process of blowing up this point, replacing the point with something like a line, it removes the singularity. So this shape here looks like two cones attached together at their vertex here at the singularity, and then this process turns it into something which looks like a cylinder where there is no singularity anymore. So these are the kind of thing algebraic geometers study, and it's a very nice topic. And a very deep result of Hironaka from the 60s says that, in fact, if you have any algebraic variety, any affine variety defined over the complex numbers, you can always run a process of blow-ups and remove all the singularities. This is an amazing statement. So this is not visual anymore. You need a lot of hard work to prove something like that. But at least in the examples, we saw how it works. But for fields of positive characteristic, a similar statement is a major conjecture in algebraic geometry. So for people who are interested in young people who want to maybe have some kind of role, like examples of problems in algebraic geometry, this is one of the examples. So you can formulate it in a very simple way. It just says that if you have an algebraic, for example, affine algebraic variety, as I defined, over fields of positive characteristics. So for example, algebraic closure of finite fields, then the statement, the conjecture says you can always resolve its singularity somehow. And so this it's nice because the statement is simple, but it's a difficult problem. Okay, so far I have talked about local kind of geometry. Meaning that I define algebraic affine varieties inside some affine space. And for example, I looked at their singularities, but there is also a global version of algebraic varieties. These are called projective varieties. They are compactified versions of affine varieties. In general, in mathematics, is well understood that if you have compact spaces, for example, if you work in topology or in differential geometry or algebraic geometry, when you have compact spaces, they behave much better because you can see everything. But if a space is not compact, that means something is actually missing from the picture. And then you will have to maybe take a limiting process to see what happens if you go toward infinity, to these missing points, to understand its geometry, its structure. But to avoid this problem, there is just a compact version of spaces. You can just directly work with these compact spaces, so you don't have this problem. And that's why people define projective spaces and projective algebraic varieties. Now, the n-dimensional projective space, by definition, is of this form, where you see that here we have n, but here we have n plus 1 coordinates. In the local case, we had n, but we had exactly n coordinates. Here, it's a little bit different. We need n plus 1 coordinates. Again, all these numbers come from our field. They should not all be 0 at the same time. And the points here in this space are defined up to this equivalence, where if you have a point and if you multiply all the coordinates with a non-zero number, we say that the point is the same. It just has different representations, different way of writing down the point. The coordinates can be different, but the point will be the same. So if they are proportional by some fixed non-zero number, then they represent the same point. So this is an abstract kind of definition, but it turns out that in fact this Pn is nothing but k to the n, and then with a copy of p to the n minus 1 added at the infinity. So for example, if we work over the real numbers and if we look at p1, then p1 will be just r, which is a line, together with 1 point at the infinity added. And that's why this is a compactification of the usual space that we are familiar with, like r to the 1 or r to the 2 or 3. So just remember that this is a compact version of these spaces. You don't have to worry so much for the moment about the formal definitions. Now that we have this ambient space, then we can define projective varieties. A projective variety inside Pn is now the solution set of a collection of polynomials, let's say f1 to fr, which are homogeneous. This is just for technical reasons. Homogeneous means that all the degrees in the polynomial should be the same. Otherwise, it would not make sense to say that a polynomial vanishes at a point, because points, their coordinates are not unique. They are represented, the coordinates are determined up to multiplying by some number. So that's why we have to take homogeneous polynomials. So an example would be just to take a linear polynomial where all the terms are just degree 1. For example, like s0 minus s1. This is a homogeneous polynomial. It defines, in fact, a line inside P2. And this line itself happened to be just a sphere. It will be, so we are working over the complex numbers. This will be a sphere, which is just P1. So over the complex numbers, P1 is the same as a sphere. But if we take a homogeneous polynomial like this, where the degree is now 3 instead of 1 or 2, this also defines an algebraic variety, a projective one. And this happens to be a so-called elliptic curve. So if you are algebraic geometer or number theorist, then you know that these kind of spaces are very important in mathematics. Okay, but for today, I'm going to mostly focus on, I look at the two-dimensional projective space, just P2, and look at algebraic varieties inside this P2. So this is basically the simplest type of algebraic geometry that you can do, which is not trivial. So we take X to be in P2, defined by one single polynomial F. The equations of this polynomial, I will even take them to be integers. And let's say the degree of this polynomial F is D. And we can also assume this is irreducible, so we don't have to decompose it. So this is the easiest. When you move beyond polynomials with one variable, this is then the easiest type of algebraic geometry that you can do. Now, we want to understand this space X from an algebraic geometric point of view, but also from a topological point of view. For example, if we look at the points over the complex numbers. So in general, we want to understand the geometry of X from different perspectives. And even this simplest kind of or most elementary type of algebraic geometry actually led to some really very fascinating mathematics. And now this story is old, it's not recent, but still is quite interesting for people who are not professional algebraic geometers. So remember that X is inside P2 defined just by one polynomial in 3 variables. We will assume that this X has no singular point. So singularity means similar to what I discussed before. So there is no strange point on this space. Now, if I have a field K of characteristic 0, so it contains in the integers, we let just define a notation here, xk. I take this to be the set of points of X with coordinates in K. So depending on what K is, we will get different set of points. The space will be actually different. It depends on the field K. So this K can be, for example, the rational numbers, or it can be the complex numbers. Depending on the field, we get different spaces. But somehow the variety, the geometric properties of these spaces will be more or less the same, even if you change your field. Now, the set of complex points of X, which is simply the set of all the complex 3 complex numbers fitting into the polynomial, they look like a donut. I can just even show you a picture. So the kind of possible spaces that you get are precisely this kind of spaces. It will be either a sphere, or a donut with 1 hole in it, or a donut with 3 holes on it, or there can be more holes. But topologically, they all look the same. So their topological structure is very simple. It cannot be any simpler than this. However, their algebraic geometry is much more complicated. So in fact, here, the number of holes can be calculated just by the degree. And this number of holes is called genus. The genus is just half of the degree minus 1 times degree minus 2. So you see that if D is 3, then G is equal to 1, which is exactly this case. Now, there are many different polynomials of degree 3, but their topological space all will be the same, just look like this torus. However, their algebraic geometric structure can be very different. So in fact, there are like infinitely many different spaces X defined by polynomials of degree 3, which are different from the point of view of algebraic geometry, but they are all the same topologically. So you see, the topology is a different type of geometry. Algebraic geometry is different. So they are not the same. They are related, but they are not the same thing. So the topological shape is simple, but we want to understand more, not just the topology here. Now, in general, it's very hard to check if xq is non-empty or not, for example. So although xc is kind of simple, at least topologically, but xq, for example, is much harder to determine. If I take f to be this polynomial t0 to the m, or if you want, you can use the notation s, or t0 to the m plus t1 to the m minus t2 to the m, then we get again this Fermat's last theorem kind of situation, if you look at the solutions over the rational numbers. But solutions over the complex numbers is easier to see what it is. Now, suppose for one moment that we have at least one solution over the rational numbers, and then we want to see what happens. In general, if the g-index is equal to 0, in other words, if there is no hole in the space, then xq is infinite. So if you have one point, you have, in fact, infinitely many. But if the g-index is equal to 1, then xq is a finitely generated abelian group. This is known as the Mordell-Weil theorem in number theory. So it has an interesting structure of its own. It's a finitely generated abelian group. But if g is more than or equal to 2, then xq is finite. This is another difficult and deep theorem of Falting's. So the first case is kind of simple. The second case is difficult, but still is not like it's very hard maybe, but the third part is very hard. So you see that even just working in dimension 2 inside these two-dimensional projective spaces, these algebraic geometric equations about this type of polynomial with 3 variables become very, very complicated. Now, I will try to say for the rest of the talk to somehow connect the geometry, the arithmetic, and the topology of these spaces X that we have. So remember that X is just defined by one polynomial, and X is inside P2. Now, in general, a very old trick to study the set of rational points on a variety, or you can make them like integer coordinates, is to do reduction mod a prime number P. And then, so you can use P and then see what kind of points you have after you do reduction mod P, but you can do actually more. Now, for each natural number R, we know that there is a finite field fp to the r with exactly p to the r elements. For example, we have fp, which is just the integers mod p, but you have more fields. For every r, you have a field which contains fp. There are so infinitely many fields here. And you can also study the solutions of our equation over these fields. For each r, we look at the points of x inside fpr. So in other words, you just have your equation, you consider it as an equation over fpr and see what kind of solutions you have. So this is theoretically a simple, very simple question. Now then, we look at the number of elements inside x fpr and call that nr. So in general, when you take R to be large and large, you expect to have more and more points. And then we put all these numbers inside a series. Sigma nr sr, here is s is a new variable. This is a very common thing in mathematics. If you have infinitely many numbers, a sequence of numbers, you can put them in a series so that the series remembers all the numbers at the same time. However, experience shows that it's better to look at this new series here, which is that you take sigma nr divided by r times s to the r, and then you take the exponential of this. You still get a power series, but with rational coefficients. And again, this power series remembers all these numbers. So if you say something about this power series, it will say something about all these nr. And this series is called the Well zeta function of x. As an example, let's look at the case when f is just t1. And in this case, we can calculate x fpr. So this f is our polynomial. And here are the solutions of this polynomial over different fpr. In fact, in this case, we can determine all the solutions. They will be just points of the form a0, 0, a2, where a0 and a2 belong to the field fpr. And of course, one of them should be non-zero to get a point in the projective space. And it's easy to count how many points you have here because we are working over a finite field. In this case, the number of points, which is nr, is exactly 1 plus p to the r. So everything is calculated simply. And then we can try to determine the zeta function, z of x, which by definition was this, the exponential of sigma nr divided by r. So here we have 1 plus pr over r times s to the r. And you can simplify this. For example, this can be turned into a product of two exponential powers. And in the end, you can simplify everything and get this power series, which you can write it down not as a power series, but as a rational function. It will be 1 divided by 1 minus s times 1 minus ps. So the s is the variable we have, p is the prime number that we have. So you see that this function says something about the space X. It says something about its actually topology. It says something about its arithmetic and also about generally about its geometry. Now, in general, for the type of X that I started with, X, remember that it's defined by one polynomial inside P2. It has no singularity. Let's even assume that it has no singularity over the complex numbers, but also has no singularity over fp after we do reduction mod p. So this is satisfied for most polynomials. Then the zeta function of x is always, so by definition, is a power series, but the important point is that you can always write it down as a rational function. Why this is important? Because a power series is potentially is a sequence, an infinite sequence of numbers. But a rational function is determined by just finitely many data, by finitely many numbers that are involved. So like here, we have just 1, there we have 1 and minus p. Upstairs, phi is a polynomial with integer coefficients, so it has finitely many coefficients. So here you have a finite set of data, but on the left, the zeta function potentially is an infinite set of information. Moreover, this polynomial that appears here upstairs, you can decompose it over the complex numbers because it has only one variable. This is the fundamental theorem of algebra. And if you decompose it, you can write it in this way for elementary reasons. It will be like 1 minus a1 times s, product with 1 minus a2g s for some complex numbers, ai. Now, the important point here is that, so the fact that you have a decomposition is nothing strange, nothing, it's just a fundamental theorem of algebra. But what is important is this, is that you have precisely 2 times g components here. In other words, the degree of this polynomial is exactly 2g. But remember, what was g? G was the genus of x, which was determined by the degree of the polynomial. It was basically, on one hand, it is something algebraic because it's given by the degree, but on the other hand, the G is the number of holes inside the space XC. So it's a topological information, it's a topological data. And so that's why this is important. So this degree is 2G because you relate something which doesn't seem to be at all related to topology. Remember that we define the zeta function by looking at the set of solutions of f over fpr for different r. We put all these things together. So that looked like a very algebraic or geometry kind of construction. But this formula relate all these things to something which is topological. And that's why here I'm saying we have geometry, arithmetic because we are just looking at solutions of polynomial over some finite field, and we also have topology. So everything is involved here. Finally, you can even say more about these complex numbers that appear in this formula, and that's that their absolute values are precisely p to the power half, or in other words, square root of p. So again, you relate the prime number p to these complex numbers, and I mean, there is no obvious connection between all these things, but this formula is the statements say something about all these topics here, and that's why it's really interesting. Now, people try to generalize this to higher dimension. This story is, in my case, in this talk, x was inside P2. So x itself has dimension 1. But people try to prove something similar in higher dimension. And usually when you go to higher dimensions, everything becomes much more complicated. But eventually this was carried out. This was done by Grothendieck and Deligne and with the help of other people. And just this effort to generalize this statement to higher dimension led to a revolution of algebraic geometry. So that's why this story is very interesting mathematically, but also historically is really very important. And so if you are interested in any of this topic like algebraic geometry, arithmetic, or topology, there is something in this story for you. If you just learn, if you look at the statements and first of all, understand what the statement says. So I'm mostly talking to young people here. Just to understand what the statement of this theorem says, understand all the data that is involved. And if you are even more serious, if you try to even look at the proof or understand some part of the proof, that's even much better. So you see that you can learn something about all these topics, about geometry, algebraic geometry, about arithmetic, about topology, and so on. Okay, there is more stuff to talk about, but I think I better stop here because I already said a lot. Thank you for listening.